Hello, computer scientists, and welcome to week 9, day 2. Today we're going to talk about indexes, specifically in MongoDB. So we are going to look at our data with and without indexes and see how that makes a difference. So MongoDB has some tutorial videos that you can find, and they do a really good job of explaining this exactly the same way I would. So I'm just going to go ahead and play that video for you first.
Welcome to the chapter on indexes. In this chapter, we're going to cover some of the different indexes supported by MongoDB, and we'll also discuss the different properties that those indexes have. In this first video, we're going to examine what indexes are and how they work. And to answer this first question, I think it's helpful to ask the question, what problem do indexes try to solve? And that is slow queries. Let's use a quick analogy to illustrate what I'm talking about. Let's say we're looking for some content on bedspreads in a book about interior design. One way that I could find this information is I went through the book page by page, looking for information on bedspreads. But this would not be very fast. I could find this information much more quickly if I went to the back of the book to the index, where I can quickly search for the word bedspread because the index is ordered alphabetically. I'll then find what page talks about bedspreads, and I can go directly to that page. And this is essentially how database indexes work. Working off the book analogy, a book, in the context of MongoDB, would be a collection. If we don't use an index when we query our collection, then the database will have to look at every single document. Creatively, we call this a collection scan, which means as our collection grows in size, we'll have to search through more and more documents to satisfy our query. In computer science, we call this an order of n operation, commonly referred to as big O of n, or having a linear running time. And that's because the running time of our query is linearly proportional to the number of documents, n, that we have in our collection. But we can do much better if we have an index. Like in the book analogy, we can use an index to limit our search space. Rather than searching through every document, we can search through the ordered index first. The MongoDB index keeps a reference to every document in our collection. Think of this index as a list of key value pairs, where the key is the value of the field that we've indexed on, and the value of the key is the actual document itself. I like to point out that this means that an index is associated with one or more fields. This means when we create our index, we have to specify which fields on the documents in our collection we want to index on. For example, the _ID field is automatically indexed for us. But if I were to write a query that didn't use the _ID field, I wouldn't be able to search the _ID index and find the reference to my documents. And it is possible to have many indexes on the same collection. I might create multiple indexes on different fields if I find that I have different queries for different fields. Like the index at the back of a book, the index keys are stored in an order. Because of this, we don't have to look at every single index entry in order to find it. MongoDB uses a data structure called a Btree to store its indexes. Btrees can be used to find target values with very few comparisons. With a collection scan, each new insertion creates an extra comparison. But with a Btree, each new insertion doesn't necessarily mean an extra comparison. For example, if I was searching for the value of 15, my search wouldn't change if I inserted the value of 5. We can plot a chart to get an idea of how many fewer documents we need to examine when using an index. You can see that when we don't have an index, we have a very linear function of number of comparisons. But when we do have an index, we need to examine far fewer documents. Before I finish this video, I would like to discuss one last topic, which is index overhead. The awesome query performance gain that we get with indexes doesn't come for free. With each additional index, we decrease our write speed for a collection. Every time there's a new document inserted into a collection's indexes might need to be updated. Similarly, if a document were to change, or if it was completely removed, one or more of our Btrees might need to be balanced. This means that we need to be careful when creating indexes. We don't want to have too many unnecessary indexes in a collection because there would then be an unnecessary loss in insert, update, and delete performance. You should now have a good idea of what indexes are, their pros and cons, and how they work.
All right, so thank you for that video. We are going to talk a little more about it. So Why would we want to index? So there's obviously searching, which is what we do a lot with databases. But even within that, we have a lot of different priorities, right? The overall theme for this course is it depends, right? So there's a lot of different things that you might want to be doing with your database, and your priorities might change depending on the project or even the use case. So if you're just searching, you have access time. So how long does it take to find something? But there's also access types, right? Are you searching for a range of dates instead of just a single date? Are you searching for certain kinds of images? Are you searching for both name and city? Or zip code and city, right? There's multiple ways to search, and it's not always just looking for one single thing. How many people live in a zip code? How many people live in a zip code that have an income less than $50,000 a year? Things like that, right? There's lots of combinations of searches that you might be trying to optimize. Also, you're not just searching. There's insertion, deletion, update, right? It depends on what you are trying to do in your database. If you're just looking at census data, you're rarely going to update that. But in a university database, you're inserting, accessing, updating, deleting all the time. There's a lot of data going in and out of a university database. So, there's different priorities that you have to think about when you're creating indices. And then, of course, there's space overhead. This obviously isn't as big a deal as it used to be when space was much more to premium, but it still is, right? Especially in, IoT devices or things like that, where you may not have a lot of space for your database, and you want to maximize what you can store on a small amount of memory. So remember, as it says, that databases contain data on a disk, right? Real life data that you're trying to use. It's not just algorithm numbers. So just because an algorithm says, oh, this one is linear and this one is logarithmic for this particular use case, doesn't mean it's always going to be the best thing for you in every use case. So you always want to remember it depends. So as they said in the video, this is a representation of an ordered index. So when we insert things in a database, they're not in order, right? They come in whatever order they are, and they're just stored on disk in whatever order we insert them. So how do we quickly search through that? In a simple use case here, we start with Alice, Bob, Charlie, Dave, and we go to Yolanda and Zelda at the end, right? So we just have a nice long list in alphabetical order, and all it does is point to wherever the actual data lives on disk. This is really nice both for individual searching. I'm looking for Phil, is going to be somewhere in the middle here, and I can even use a binary search to try and find that really quickly. It's also really good for ranges, right? So say these are birthdays. I want to find everybody born in the year 1990. I know it's going to start with 1990 January 1, and it's going to end with 1990 December 31st, right? I can get a chunk of data out of here, and it'll just pull all those arrows to where the data actually is, and I don't have to go through the entire big list looking to see whether every single date is inside the date range I'm looking for. I can just go to my index, start with the beginning of it, go to the end of it, and pull all that data, just look where the arrows are pointing. So ordered indexes are really great for searching both individual and ranges. Hash indexes are slightly different. So this is, if you remember the hash function that we talked about with when we were storing passwords, it's a one-way mathematical function that gives you a number based on whatever data you have. So there's lots of different ways to do it. You can use mathematical functions like modulus is the one that we used, where 15 modulus 5, what is the remainder of that? Is 0, right? 20,005 modulus 5 is also 0, right? So lots of different numbers have the same modulus, but if you just know that the result of that is 0, you don't know which number you came from, right? So it's a one-way function. But you can use that in a hash index as well. So the example here is, say your key is first name, right? Is Alice in this case. So here's a one-way function. Let's get the ASCII values of the letters. So A, I don't remember what it is. Maybe it's 80. L is 104. I is 29. Whatever they are, I take the ASCII values of all these letters. I add them up, and it gives me some number, 528. So I make a bucket. I call it bucket 528, and I put all of my data with the same hash number in that same bucket. Okay? So it might be, say, 10 different things. Alice, Frank, and Bob, right? Notice that they are unrelated. They're not all A names. They're not all the same length. They have no similarities except if I add up all of the letters, right? Then they give me the same number. What makes this super fast is the function of adding up all their letters is really, really fast. So if I'm looking for a name Jose, and I want to find what bucket it's in, all the data about Jose, all I have to do is add up the letters in his name, and then it gives me a hash 528, and then I only have, 5 or 6 other items in that bucket to look through. Instead of having to look through every single item in my database, I just hash the first name and put all the data for that item in that bucket. So depending on how many buckets I want to have, depending how my hashing function works, I could have 10 buckets. If I don't have a lot of data, I could have 1,000 buckets, right? All I have to do is hash my key, and it'll point me directly, very quickly, to a bucket that is much, much smaller subset to look through. So this makes it really, really fast for individual search, but it obviously makes it really, really bad for arranged search, right? If I want to find all the people whose first name is Alice, they're all going to be whose first name starts with A, they're all going to be in different buckets. Alice, Avery, Adam, right? All those names, when I put them through a hash function, are going to give me a different number at the end of it. So all the A names, or most of them anyway, are going to be in completely different buckets, and I'm just going to have to go search through those buckets anyway. So if I just want to find one thing, hash indexes are super fast. If I want to find a range, they're really, really bad. And that's why they're not really used for database keys. That's just a different example of a way you can index data that is commonly used, but not so much in databases because it doesn't fit a lot of use cases in databases. So binary trees, and binary search, this is what I talked about a few weeks ago. So this is really, really fast for searching both ranges and individual items. So because it's binary, right, the maximum number of levels is going to be log base 2 of the total size of your data. So if I have 1 million items in my database, the maximum number of comparisons I'm going to need to make is 20, right? So think, for example, of I have 1 million people in my database, and I'm looking for somebody with the name Melanie, right in the middle. It's probably going to take me 500,000 comparisons to find Melanie, right? I got to start at one end, and just go through it one at a time. If I don't have an index, I got to say, is Alice Melanie? No. Is Adam Melanie? No. Is Bob Melanie? No. Is Charlie Melanie? No. Is David Melanie? No. Blah, 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 all the way through until I actually get to Melanie, about halfway through my million items. That's going to be slow, right? But if I have a binary tree like this, I go right to the middle. I say, I'm going to start with M because I know that's the middle letter of the alphabet, right? Is Max equal to Melanie? No. I know that Melanie is slightly larger than Max, so I'm going to go down to the right, right? So that has eliminated everything from the letter A through the letter L. I don't have to search those. And then halfway between M and Z is, I don't know off the top of my head. Say it's, I don't know, R, right? Well, Melanie is less than R, so I'm going to go to the left. That eliminates everything from R through Z. So again, this is how binary search works. I remove half of the items that I no longer have to search every time I go down. So in the example on the screen here, let's say I'm trying to find the number 7, right? I know that I have the numbers 1 through 14, right, in my database. So I'm going to start with the number 8. Is it bigger or smaller than 8? Well, I know that 7 is smaller than 8. So I have eliminated all of these nodes already. I don't have to search them anymore. The next number down is 3. Okay, well, I know it's bigger than 3, so I've eliminated everything over here. I go down to 6. I know it's bigger than 6. And there I get to 7, right? If I had to do a linear search, it would have taken me 7 steps. 1, 2, 3, 4, 5, 6, 7. Here it's taken me 4 steps, right? Doesn't seem like a huge benefit for a small amount of data, but when you get into the millions, obviously 20 is faster than 500,000. So what databases actually use are Btrees, and these are a variant of binary tree, right? So one of the problems with a binary tree is deleting and inserting new data, right? When you insert new data into a binary tree, you have to rebalance the entire tree every single time, right? So if I put in the number 9 here, right, if I insert a new node with the number 9, I know that it's bigger than 8, so this node here, 10, is going to become, or it's not going to become, but it's going to get pushed down by the number 9. And then I have to look at this whole bottom branch of it and decide how am I going to split it up now that I have a number 9 here instead of a number 10, right? I don't want to just push all of it down to the right-hand side, because if I keep doing that, I'm just going to end up with one long chain, 9, 9.1, 9.2, 9.3, 9.4. It's just going to be a linear search again. So once I insert a number 9 here, I have to look at all this data over here and decide whether it needs to be rearranged. And if I keep doing it, do I need to actually rearrange some of this as well? So binary trees are great for searching, not so great for updating and inserting, right? If I change this number 6 to a number 50, right, I update my database, boy, I'm going to have to do a lot of rebalancing in this tree. So inserting and updating is hard in binary trees. So that's why they came up with this idea of a B-tree. And B-trees are a little bit tricky to wrap your head around. I could spend an hour, talking about it. I'm just going to give you a quick overview, but, Wikipedia obviously has a great entry on it, and there's lots of videos on Btrees. I'm never going to test you on how Btrees work. I just want you to understand why they are good, right? So, like everything in this class, I'm much more interested in why and how than what, right? No memorization. I just want you to understand it. So a B-tree is a variant of a binary tree where everything is very well balanced. And what you have is boxes like this, which hold a bunch of items inside it. So instead of just one item in each node here, like a binary tree, in each node here you have several items. And your node does not have to be full. You'll notice that some of these don't have full nodes of items inside it, right? Each one should be about half full, but it doesn't have to be completely full because it makes inserting much, much easier, right? So in this example, you can see that 1, 2, 5, and 6 are stored in the leftmost node, which is less than 7. And then 9 and 12 are stored in this middle node, which is between 7 and 16. And then 18 and 21 are stored in the rightmost node here, which is greater than 16. So if you had a bunch of numbers like 10 and 11, they would either, well, first they would be pushed in between these two in this node. But if you kept adding more, 9.5, 9.6, 9.7, 10.1, 10.2, 10.3, 11.1, blah, 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 and this started really filling up, right? You would just add a new node down here, a new box, with a whole bunch of items inside it that would fit between 9 and 12, right? So it makes inserting really, really easy. And updating as well, right? So say in this example where I said 6 turns into 50, you have to rebalance this whole tree. It's going to take a lot of time. If this number 6 turns into a 50, all you got to do is say, oh, it no longer belongs in this box because it's greater than 7. It's greater than 16. Go down to this box. It's greater than 21, so stick the 50 over here. It's logarithmic again, right? We didn't have to do linear. We didn't have to check it against every single other item in the entire database. We didn't have to rebalance any of the boxes because there was an empty space here already. So all we had to do was change this number to a 50, look at our root node here, say bigger than 7, bigger than 16, bigger than 18, bigger than 21, boom, stick it right there. So again, logarithmic for insert, logarithmic for update, logarithmic for search. So it is not quite as fast at searching an individual item as for a binary tree is, but it is way faster for inserting and updating. Way, way faster on average. Remember, these are all averages, right? So some of the advantages of the Btree, it keeps all the keys in sorted order, right? So if we are searching for an individual item, or if we're searching for a range of items, right? Say I want to find everything from 5 through 10, right? It's still easy. It's still 5, 6, 7, 9, right? They're all right next to each other. Even though they're in different nodes here, they're still in sequential order. It's not all over the place. So that makes both individual searching and range searching really fast. Again, uses hierarchical index, so you only need a logarithmic number of disk reads, right? As I mentioned, the blocks themselves are only partially full, right? As you can see, some of these have empty spots, which is great because it makes insertion really fast and updating really fast. And it keeps the index balanced with a recursive algorithm. So I'm not going to get too much into how it rebalances itself. Again, I would highly recommend looking at the Wikipedia article and looking at some videos, but it keeps the entire tree, the number of nodes and the number of levels and the number of items in each box balanced automatically based on how many numbers you have in order to maintain that logarithmic speed. So the another nice thing about it is, there's no theoretical maximum for insertions and deletions because of the automatic balancing, the half-full boxes, and the way it's sorted and organized. You can just keep inserting and deleting and updating as much as you want. and it will always be logarithmic. So those are the huge advantages. That is why we store items in a database in a Btree format. So again, this is just a visualization. You know, if I had 1,000,000 documents and I was looking for Xavier, I'd have to start with A, B, 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 C, 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 right? I have to search all the way through the end. But for a Btree, it would be logarithmic. So one of the problems, right, is multiple, when you're looking for multiple pieces of data. So for example, zip code and income, right? Indexes are focused on the first part of it, right? So if I'm looking for name and hair, right, Xavier and Brown, it's really fast, right? I can find Xavier in 20 searches if there's 1,000,000 documents, I can find Xavier in at most 20 searches, and then within that, you know, brown hair, if there's 10 Xaviers, right, I can find brown hair pretty quick. But I cannot find all the people with brown hair using this index any faster than linear search, right? Because I created the index first on name and then on hair color, if I'm just looking for hair color, this index doesn't help me at all. So indexes have to be focused on one thing first, and it doesn't matter if you have, you know, zip code and then income level by zip code. It doesn't help you find a range of income levels by itself. You still are going to have to look through the entire database unless you create a new index just on income level. So as they mentioned in the video, indexing is not free, you know, so why don't we just put an index on hair color and, you know, first name and income and zip code and, you know, everything you can possibly think of? Well, because it takes a little bit of storage for every one, but more importantly, every time you make a change to the database, you have to update your indexes, right? So if you have 50 different indexes, right, you're going to have to do a logarithmic update in the best case scenario 50 times. So if you have 10 million items, right, that's still going to take a lot of time to do those 50 logarithmic updates. So why do we add indexes? Well, reads are much faster, right? So when should we add an index? Depends on your use case, right? If you are never going to search by hair color, don't add an index on hair color. It's not going to help you. It's not going to make anything faster. Or if you only search 1 out of 1,000,000 times on hair color, who cares if that one search is slow, right? It always depends on your use cases. So, and you can always change it too, right? Like that's the nice thing about indexes is they only take a little bit of space, excuse me. And yeah, they take a while to create if you have a lot of data, but you know, if at first you think everybody's going to be searching your database by first name, but it turns out that everybody's using hair color instead, right? You can analyze your database usage and add a new index on hair color at any time. But definitely when you're building your database, you don't want to add the index until you put all your data in, because otherwise it's just going to be slow. All right, so we are going to create our own indexes. And so the first thing that we want to do is we're going to download the Compass program so that we can run text-based queries on our data. So let's do that. All right, so we're going to quickly install MongoDB Compass. So what we're going to do is go to just Google MongoDB Compass, and it'll come to this page. I'm obviously on a Mac, but the PC version is exactly the same. So let's just go ahead and go try it now. You can see slightly grayed out is the version is 1.20.5. Platform is OS X, right? So you might be on Windows. And I'm going to click download. Okay, as soon as it's finished downloading, I'm going to click it, and the installer is going to start. So I'm going to skip the installer so you don't sit here and watch it, and I'll come back when it's done. All right, so here I am in MongoDB Compass, and again, this is the Mac version. The PC might be slightly different, but the functionality is the same. So I need to paste my connection string. So I am going to go into my cluster, click on connect, and it doesn't really matter what I select here because the connection string is going to be the same. So I'm going to copy my connection string and go back into Compass and paste it here. So I have to update my password again and click connect. Again, if you used a password with special characters, you're going to have to use the URL encoding for those. But you can see that all of my databases are here now. And, you can, just like in the Atlas, the browser-based version, you can see all of your data here. All right, so I have gone into the sample mflix database, and I'm going to click on the movies to see exactly what we can see. Let's see if there are any indexes already on this. So there is an index on ID that is created by default in MongoDB on every single collection that you have. There's always a default index on ID, because the IDs are created for you. There's also a text index here, and you can see that it is on cast, the plot, the genre, and the title. All right, so we don't want to use any of those because we want to first do a search that has no index on it. Then we are going to create an index and see how much difference it can make. So let's go back into the list of documents and movies. And up here is our little search bar. So you can think of this as select star from movies where, and we're just going to put in the where clause, right? So we are going to look for, let's say, movies that are rated TVG, right? So like this right here. So let's create our where clause. It's going to be, we're looking for movies that are rated TVG. Okay. And you can see 23.5 thousand documents in this. So let's go ahead and click find. And it's going to come back with TVG, TVG, TVG. So all of these are rated TVG. So it found a whole bunch of documents, 59 of them, in fact, that are rated TVG. So how well did it do? The nice thing about MongoDB is it'll tell us right in Compass, right here. If we click on Explain Plan, it tells us it retrieved 59 documents, did not examine any indexes because there's no index on rating, and it had to examine all 23,539 of them to search for this rating, right? Because it literally had to step by step through every single document to see if it's the one we wanted, all right? So still pretty quick, 17 milliseconds. 23,000 documents is actually not that much, and the servers are pretty fast, but I bet we can make this even faster if we add an index. So we want to build an index on the rated field and then run our query again. So let's go ahead and click on indexes. We're going to create an index. Let's call it ratings. We are going to select the rated field. We want to do it ascending. Descending doesn't really matter in our case, but we're going to select ascending. And we could add another field, but we're not really interested in doing that right now. We're just going to search on ratings. And then there's a bunch of options. So this is kind of interesting, right? We could build the index in the background. So if we have a heavily used database that is requiring a lot of reads and writes, and we need to add an index to it, we don't want to just lock the database for an hour while it's building an index, right? Because it has to move things around to build an index. So you can actually have it do it in the background as it's available. Pretty cool feature of MongoDB. Create unique index, obviously, primary keys, stuff like that, has to be unique. TTL is actually really cool as well, right? So if you have a log database of events and it, gets really, really big, it's like, measuring, or it's writing log events for, I don't know, a web service, right? And if it's several megabytes a day or, gigabytes a day, you don't really care about web events that happened 6 months ago if, you're never going to look at those logs again. Or you could, export those to a file and store them somewhere else, but you don't need them live in your database. You can create an index in MongoDB that will automatically delete old data. You create an index based on the date, and then you say anything older than 6 months, delete it, and it'll have this thing in the background that will delete automatically anything in your database in this collection that is older than 6 months old. Right? You can do it on any field. It's pretty cool. And then the other ones, I don't want to spend too much time on this. You can click on the little eyes here and get more information about them. We're not going to use any of those. I just want to show you how an index works in MongoDB. So let's go ahead and create that index. It's going to be pretty quick because we don't have a huge amount of data and nobody else is using our database. And so it's already finished. So let's go back to our documents here. We still have our query in here. So let's go ahead and run it again. And this time, if we click Explain Plan, it only examined 59 documents, right? Because we had an index based on what we're looking for. So it knew exactly where to go to find anything rated TVG. It had an index specifically for that. So it only had to examine those documents that are rated TVG, and it executed it in 5 milliseconds as opposed to 17 milliseconds before. So obviously, creating indexes on data is very, very useful for when you're querying a lot of data. And what I would like you to do this week, for Tuesday now, is once you've done Tuesday's assignment, I would like you to add some indexes, try them out, see how they work. And in D2L, I just want you to submit 2 screenshots, a before screenshot and an after screenshot of your searches without your index first and with your index second. So this, you would just take a screenshot of this. You can use your phone if you want. I don't really care. I just want to see that you understand how different it is when you do a search without an index and then with an index. And of course, your code is also due on Tuesday from this Tuesday's assignment. If you have any questions, email me or hit me up on Discord. Have a great week.